Okay, so hi, it's Mrs. Allen here, and I'm just going to go over a couple of the problems on evaluating limits part 2 with complex fractions and a couple of piecewise functions. So the idea with complex fractions is that in the complexity, you want to see if you can simplify the complex fraction first and then take the limit. In many cases, you're able to take the limit and of a very easy expression. So if you look at the first example, what I did for you is I took the denominator and I simplified I combined the denominator fractions and I got what you see here. So then what I did is I took the numerator x and put it over that simplified form, and then I multiplied by the reciprocal because you're dividing x by a fraction. So instead of dividing, change it to multiplication, multiply by the reciprocal. So I get negative 2 times 2 plus x. So that's what I'm going to be taking. That yellow expression is what my limit, wrong pen. So the yellow expression is equivalent to that. All three of those are equivalent. So we've just messed around with it a little bit so that we can take the limit. So we get the limit is equal to then negative 2 times x is now 0. X is approaching 0, so we do a direct substitution. 0 plus 2. So I get negative 2 times 2, and I believe it was negative 4 for an answer. Let's see if that's what we got down here. Negative 4 it is. Okay, cool. All right, it's late and I don't want to make any mistakes as I pass this on to you. So now number 2 is really the same expression as number 1, except you have a different plug-in value here. Where you were plugging in 0 for the first one, the limit as x approaches 0. Now it's the limit as x approaches negative 2. So I'm just going to take the expression and I'm going to plug in negative 2. So I get negative 2 times the quantity. So remember what we're doing, we're plugging in this x value with negative 2. So I have negative 2 already out front, and then it's 2 plus negative 2. Okay, that's the x value we're going to plug in. So we get negative 2 times 0. So our answer here is 0 for the second one. And I think that's what I noted on the last one when I scrolled down the last time. Okay, so there you go. So then as you look down at the next couple of examples, I have worked out the fraction itself. So I started off with, let's color code this a different color. So we have this. Now, so what I did is I combined the denominators with a common denominator of 1 plus x. You got to make sure in this top part that you get the, instead of just saying minus 1 plus x, you've got to minus the quantity of 1 plus x, okay? So then I'm going to combine the numerators here to get just negative x. And then I'm going to do the same thing where I'm going to multiply by the reciprocal. So what you see in orange then is equivalent to this. Once we get our simplified expression, even though, I guess I should go back and say this, we can go ahead and take the limit now, but even though the whole problem here is that if we put negative 1 in here and we put negative 1 here, what we end up with is 1 over 0 here. So that's a problem. That's undefined. So we're not able to work with that form of the expression. So that's why we've got to simplify the expression. So it's not indeterminate, it's just undefined at this point. Now, if we look and put negative 1 in here, then that's certainly going to be undefined. And so once we manipulate our expression, we get this simple little polynomial. When we plug in, then we get negative 1 times the quantity 1 plus negative 1, which gives us a value of negative 1 times 0. So our answer here is also 0. Okay. Okay. Now, with this one, I did the next one, number 4, a little bit differently. With a complex fraction, I'm multiplying by the LCD over itself, thus multiplying by 1. So what I'm going to do here is I'm going to distribute the LCD to both terms, and then I'm going to take this denominator and I'm going to just scoot it over in the denominator of the fraction. So now I have the limit as x approaches 0. So now I have this 1 because the denominators cancel here. But when I multiply that first time around, I'm not going to cancel it like that, but you get the picture. 1 plus, then it's going to be 1 times negative 1 plus x in the top and in the bottom. So that's kind of pretty, right? You bet it is. X times negative 1 plus x. So now simplifying the numerator, we're taking the limit as x approaches 0 of, we just have x in the numerator over x times negative 1 plus x. So we're going to cancel the x's, right? Cancel the x's, and we get, those are 1's then, oh, 1's. And we end up with, we're taking the limit as x approaches 0 of 1 over negative 1 plus x. And so we end up with, scooch this over here, it's equal to 1 over negative 1 plus 0, or it's equal to negative 1 over 1, which is negative 1. Okay, so pretty nice little answer there. Okay, now looking at a couple piecewise functions, and these are pretty quick. If you're not really great at looking at quadratic graphs and what they look like at this stage, just maybe get a little bit of practice with your calculator if you haven't been doing that over the summer, so you can kind of see that equation looks like that. Okay, so you can see that where x is not equal to 3, it's the quadratic. That means you can't use 3. If you use 3 in the equation, you get 2. If you plug in 3 into that highlighted pink equation, you're going to get 3, 2, the ordered pair. So now we're just looking, what is the limit as x approaches 3 on this function? And you notice that I have this point down here, 3, negative 2. It's because the second part of it is defining the y value as 2, negative 2, when the x value is 3, thus the point 3, negative 2. So that does nothing for the limit as x approaches 3. That's just a point. It is a function still, f of x is function notation, because it passes the vertical line test. But that point of singularity does not affect the limit. So you see my red arrows as they're pointing towards x is equal to 3. The limit from the left is 2, and the limit from the right, here's, oops, the limit from the left, here's the left, is 2, and the limit from the right is 2. Therefore, the limit is equal to 2. Okay, so from both directions. Now, I'm going to give you a graph of the next one, but you can see what the limit is without even, you don't even have to compute once you have the graph for this. You see where we have that hole? So the limit as x approaches 0 is going to be, you're saying that to yourself. I'm waiting for you to answer, and I realize that I have no class in front of me right now. Just kidding. So anyway, the limit's going to be negative 1. Now, I could formally write that out, but that's what the limit is. And then as you look down here for number 7, from the left, from the right, so the limit is going to be 1. The limit as x approaches 3 of f of x. F of x is the piecewise function. Notice that when it's split up, it's the equation y is equal to x minus 2. But see the point 3? 3 is coming from the y value is 3 when x is 3. So it's the point 3, 3. It's a point that's not on the line, but just because there's a hole at 3, 1 doesn't take away from the fact that the function value is approaching 1. Okay, so there's that one. And one more down here. And we have this one, and so the limit as x approaches 1 of f of x here is then going to equal, so you see where we have the quadratic upside down. When x is not equal to 1, you see I have a hole at 1, negative 1, but as we have this little point, 1, negative 2 down here, it keeps the function a function. It doesn't violate the function rule. So we're just going to say the limit as x approaches 1 from the left and the right is the same. It happens to be negative 1. And it's right at that hole. So now you have a couple others of these. I'm just going to remind you that remember to factor as you're looking at the rational expressions. Some of these are a little bit of a review from yesterday's lesson. But here I'm going to do the same thing. And there's the answer is 5 here. Pretty easy, pretty nice. You see, it doesn't affect the limit from the left and the right. As you're approaching 1, it's still going to be 5. Okay, so if I look at this one, just one real quick one. So the limit as x approaches -1. As x approaches -1, I'm going to factor the numerator, and the denominator is already prime. X plus 1, I'm going to usually take a shot to see if x plus 1 is a factor. X plus 3, it certainly is, right? X plus 1 times x plus 3, these cancel. And rather than write something out again, let's just go ahead and do a direct substitution. The only thing that is left here is the x plus 3, so I'm going to plug in -1 plus 3, doing the direct substitution, and I get a 2. And I have the solution key down there so you can check that out. This is the line x plus 3, so you know it's just going to be like this, and but when x is -1, there's going to be a hole in the graph right here, right? And that should be correct at -1, 2. And I said I wasn't going to draw, and there it is. Okay, and you have 2 more of these here. Remember that when you see the square root, when you plug in 1 here, you're going to get 0 over 0, so it's indeterminate. So what you're going to have to do is multiply by the conjugate over itself. And the nice thing about that is when you do that, I'll make this a little bit bigger. In the numerator, we're going to get the limit as x approaches 1 of x minus 1. That's because we have the difference of 2 squares there. That's just going to be square root of x times square root of x. You could FOIL it if you want to double check it. And then at the bottom, we don't want to multiply this through. We're going to leave it just like this as x minus 1. And if you look at this, oh, it kind of makes sense now when you think about that, because we want the x minus 1 to cancel. I gotta hurry up. This video is getting kind of long. It takes up so much memory. Okay, so now we get the limit as x approaches 1 of 1 over square root of x plus 1, which is equal to 1 over square root of 1 plus 1, which is equal to 1/2, or 1 over 2. Okay, you can check the graph out below. It's you'll recognize it when you see it down there, that the x value is 1 when the y value would be 1/2 at the hole. So when you see your graph, 1, 1/2, you'll see a hole right there, okay? And then for this one, we're going to multiply by the conjugate. And the first one, we rationalize the numerator. We're going to rationalize the denominator here by multiplying the square root of x plus 6 plus 3 over the square root of x plus 6 plus 3. So now when I do, I'm going to get the limit. I'm going to write it down here so I have a little bit more room. The limit as x approaches 3. The limit as x approaches 3 of, okay, so we're going to leave the x minus 3 in the top, and we're going to write then the square root of x plus 6 plus 3, and then in the bottom, we're going to multiply the difference of 2 squares, which is then going to give us x plus 6, and then that's going to be minus 9. So let's go ahead and stop for a second, simplify that to x minus 3, right? That's kind of cool. Cancel these two. And in the interest of time, I'm just going to substitute. Looking at what I have left is this. So I have the limit is equal to then the square root of 3 plus 6 plus 3, and that's it, right? So 9, square root of 9. 3 plus 3, and our answer should be 6. So that means that we have a hole in the graph at 3, 6, right there. The x approaches 3. Let's see what the graphs look like. And you see the point is 3, 6. There's the one that we had before. Okay, hope that helps you guys with piecewise functions and some of the complex fractions. Okay, so I know it was kind of quick. If you have any questions, please contact me. Have a great day. See you later.